Sure. Oh, Bartek turned the recording on. So, welcome all at the TCS seminar at Jagiellonian. Today we are very happy to have Jean Cardinal with us, professor at the Université Libre at Brussels. So Jean is known as a computer scientist, and I know him for his contributions in computational geometry. I think this is his main research theme. From my experience, the usual thing is that Jean proposes a problem with some geometric setup or inspired by geometric setup, but often it's a pure graph theory or poset theory, and it's always fun. So today I know that Jean is planning to give a talk on rectangulations. This is a topic initiated at least at the last Order and Geometry workshop. Thank you, Jean, for joining us. It's great, and the floor is yours.
Okay. So do you see my slides?
Yes.
Perfect. Thank you so much, Piotrek, for this very nice introduction, and Piotrek and Bartek and people there for inviting me to this fantastic seminar. It's really a pleasure. And indeed, that's what I'm going to do, talk about combinatorics of rectangulation. So first of all, I'd like to mention and thank my collaborators on this project. So this is indeed a work that was started at Order and Geometry, the famous workshop organized by Stefan Felsner and Piotrek Micek. And there was a group of people there, including Andrea Zinowski, Stefan Felsner himself, and Eric Fusy, who started to discuss rectangulation, and we started sharing what we knew on rectangulation and thought that we should do more. And then more recently, last March, I actually discussed this topic with Vincent Pilot. And well, there's sort of a follow-up things going on with him. So I would like to thank all those people and the organizers of the workshop, and Stefan Piotrek, and Namrata and Torsten Münzer also organized the latest workshop. And okay, so rectangulations and combinatorics, what do I mean by this? First of all, rectangulation. Rectangulation is a tessellation, a decomposition of, say, a square. Maybe you can think of it as the unit square into axis-aligned rectangles. So the illustration there is from Theo van Doesburg. In the 1920s, there were a bunch of Dutch designers and artists who like geometry, and this painting, it's a painting, is a good example of rectangulation. You can see that this big square is split into axis-aligned rectangles. We look at generic rectangulations in which no four rectangles share the same vertex. So the graph there formed by this rectangulation is a degree 3 graph. And there will be n rectangles, so finitely many rectangles, and we'll say the rectangulation has size n if it has n rectangles. So that was for rectangulations, what I mean by rectangulations, and we'll give more details later. What do I mean by combinatorics? And I'll try to show you like 3 distinct combinatorial point of view on the topic of rectangulation. One is the bijective point of view, which is putting bijection classes, equivalence classes of rectangulation with other families of combinatorial objects, which will be in our case mostly with classes of permutations, typically classes of permutations that avoid a certain pattern. Okay, so there's the whole business of doing bijection between combinatorial families in order to count them, of course, and to understand them better. And sometimes those bijection preserve some features of the classes or parameters and so on. The order theoretic point of view on this will involve the weak order on permutation and so-called lattice congruences. So these are equivalence relations on elements of partial orders. There will also be geometric partial orders from typically adjacency of those rectangles will give us posets, which will allow us to construct those lattice congruences. So that will be for the order theoretic part. And then from order theory, from posets, you can construct polytopes also. And I'll explain how lately, together with Vincent Pilot, we had a deeper look at polytopes whose vertices are rectangulations, right? Pretty much the same way as associahedra have vertices that are one-to-one with triangulations. So this is the program for this talk. And well, let's start with the simplest, maybe the beginning. Just plain permutations, right? Permutations of n elements. There's a well-studied natural partial order on permutation, which is obtained as follows. So every permutation has a set of inversions, right? Which are elements that are in some order in the permutation, but the first one is really larger than the second one. So every permutation has a set of inversions. And if you look at the inclusion posets of these sets of inversion, you get what is known as the weak order on permutation. Okay, so this is the picture on the left there. At the bottom, the smallest ones has 0 inversion. This is the identity permutation. And the maximum number of inversion is achieved for the mirror image of this identity permutation. So in case n equals 4, illustrated here, you get 1, 2, 3, 4 at the bottom, 4, 3, 2, 1 on top. And now the cover graph, which means that those pairs that are like directly ordered, without transitive action in this partial order, are those that differ by a single inversion, meaning you add or remove exactly one inversion. And the only way to do this is by an adjacent transposition, right? So you have 2 contiguous elements and you swap them, right? So you can see there that 1, 2, 4, 3 is obtained by exchanging 4 and 2 from 1, 4, 2, 3, right? So the cover graph of this weak order is really the set of adjacent transposition in pairs of permutation. And there's a really cool thing about permutation is that if you use the word notation, so if you just look at the description of permutation as we usually do and take this as coordinates of points in space, actually you should use the inverse, but it's kind of a detail. And you take the convex solve of those points, then you get a polyhedron whose skeleton is the cover graph of this weak order, right? And this is the well-known construction. So some people say it's been actually implicitly looked at since the 1920s or so. It's been popularized by 2 French researchers who gave it its current name, permutahedron. And this is sort of the mother of all examples of the polytopes that we're going to see later. There's a family actually of polytopes that are called generalized permutahedra, also known as polymatroids in combinatorial optimization. Some people prefer to call them deformed permutahedra that are all obtained by deforming this permutahedron. And by deforming, I mean changing the right-hand side of the inequalities defining the hyperplanes, defining the facets, right? So if you move up and down, or towards the origin or away from the origin, some of the facet, you get generalized or deformed permutahedra, and you actually get all of them like this, right? So this is sort of an important, the base polytope to construct many others that are really interesting. And I'm going to do this for rectangulations. Okay, the next typical thing that we want to know before delving into this is the associahedra, and whose vertices are associated with binary trees on n vertices, okay? So by binary tree, I mean a rooted, oriented binary tree, like a binary search tree in computer science. And so you have internal nodes and then you have leaves. There's exactly n internal nodes. And these are counted by Catalan numbers. This is a well-known piece of combinatorics. And there are numerous bijections, between Catalan families. Richard Stanley has a whole book on them. So there are bijections with dig paths, for instance, there in the middle, and triangulations of a convex n-gon or n+3 gon, if you want to say, have the exact parameter. So in dimension n, you would have the convex n+3 gon, and all triangulations of this n-gon, they're also counted by the Catalan numbers. And so there's this bijective point of view, lots of Catalan bijections. There's an order that's associated with those objects that's called the Tamari lattice, and there's a polytope that's also associated with those objects that's called the associahedron. And I'm going to review this right now because this is really what we are going to build upon. This is the classic example of the way to go to construct those polytopes. So first of all, the partial order, the lattice. Let's consider every binary tree on n internal node as a poset, okay, as a partial order, and just look at the label every node in symmetric order, okay? So if you take this binary tree on the left, it's really this thing. I redrew it with nodes labeled from left to right, okay, symmetric order. So left child, root, and right child, okay? So 1 is the smallest, and then you get 1, 2, 3, 4. So you do this for all binary trees on an internal node, and you look at all linear extensions of each of those binary trees, okay? So for this one, for instance, you start by the bottom, smallest element, and you get 2 linear extensions because you have the choice picking 2 or 4 first, and then you got 4, 2, 3, 1, or 2, 4, 3, 1. You see this? So 2 linear extensions of this partial order that has the shape of a binary tree. Now do this for all binary trees on n nodes, and say that 2 permutations are equivalent if they're linear extensions of the same binary tree. And what you get is this picture on the left. So I drew the weak order on permutation, and then I glued together those permutations that are linear extension of the same binary tree. And they're all, 2 binary trees don't have the same linear extension. So it's a partition actually of the set of permutations. And it's very structured, right? So you see those two linear extensions here, 4, 2, 3, 1 and 2, 4, 3, 1. They're here, 4, 2, 3, 1, 2, 4, 3, 1, and they glue together. Now take the weak order and collapse all those classes of permutation into one single node. And then something occurs that you get another partial order, which is also a lattice. And now it's 1 to 1 with binary trees, okay? So you can label the nodes with binary trees. You get a lattice on binary trees. That is called the Tamari lattice. Okay, and you get a lattice because this equivalence relation, which is being the linear extension, being 2 linear extensions of the same binary tree, this is a lattice congruence, right? If you collapse the equivalence classes, you get a new lattice. And this one is called the Tamari lattice. It's been known for a long time. The first time it appears officially is in Dov Tamari's PhD thesis in the 50s. And then people realized that it was something interesting in many other contexts. It was first studied in the context of algebra and topology, and it revealed useful things in many other contexts. A nice way to think about these congruence classes is to look at the corresponding geometric fans. So on the left of the picture on the left, and I would like to thank Vincent Pilot also for these very nice pictures that I'm showing to you. It's very gifted for that. Here, what the picture shows is the arrangement, so-called the bread arrangement of the type A Coxeter arrangement of hyperplanes. These are all hyperplanes of equation xi equal xj for all pairs ij. Now, if you think about it, every chamber of this arrangement that are depicted there must correspond to a permutation. This is the bread fan. This is in dimension 3, so these are permutation of 4 elements. And this congruence, so this idea of collapsing equivalence classes of permutation has a geometric interpretation on this fan. This is gluing together cones of this fan, like chambers of this central hyperplane arrangements together to get these. And you can see there that, for instance, the yellow this yellowish hyperplane used to cut this chamber that lies in front of you into 2 parts, and now it's glued together because there is more than one linear extension to this binary tree, right? So every linear extension corresponds to one simplicial cone like this, and then they glue together this way. And now there's a polytope, right? The next thing is, so we have sort of this now geometric interpretation of this congruence. And if you interpret this as the normal fan of a polytope, you get you get the associahedron, okay? So you get that all these glued together cones are now the normal cones this polytope. So each of those cones correspond to one vertex of this polytope. And you get what is known as the associahedron. The edges of these polytope correspond to, again, remember on permutation, they would correspond to adjacent transposition. Now they correspond to rotations between binary trees. If you map, instead of binary trees, you draw the triangulation of a convex n+3 gun, you get diagonal flips there on the edges of the associated. So this is, again, very famous construction. It used to be, I mean, it's still called Stashev polytope because it was like really studied by Jim Stashev in the 60s, also in more topological context. But it now appears in many pieces of combinatorics and mathematics, including cluster algebra and even physics. So what did we do there? We had equivalence classes of permutation glued together, and then it has nice properties and you can extract a polytope. So there's this general notion of a lattice congruence. So you take a lattice like the weak order on permutations, and you look at an equivalence relation. And an equivalence relation is a lattice congruence if it respects the joins and the meets of the lattice, right? So there's the formula there, but it's really saying that it doesn't matter what equivalent element you pick in the equivalence class, the joins and the meet remain the same, right? So whenever you collapse those equivalence classes into single elements, you get another lattice. And this lattice is the quotient of the initial lattice by this congruence, okay? And this construction, these different steps, that starting from a congruent, we looked at the fan, you know, of the weak order. We glue together the fan, and then we extract a polytope out of this. This can be done systematically. Whenever you have a lattice congruence, you can, of the weak order, you can do this. So there's a very recent theorem, I mean, relatively recent theorem from Vincent Pilot and Paco Santos that says that for any congruence of the weak order on permutation, right? So this equivalent relation that preserves joins and meets, if you glue together the cones of the bread fan corresponding to the congruence classes, you get the normal fan of a polytope, right? So you can always construct a polytope whenever you have a congruence of the weak order. And so Vincent and Paco Santos call them quotientopes, right? Because they correspond, like the vertices are one-to-one with elements of the lattice quotient, right? Which is obtained by collapsing, replacing those equivalence classes by a single element in the lattice, okay? So this is a very general construction. It's a powerful one, and the standard application of this construction is the associahedron, but I'll show you that we can do more. Any question at this stage? No? So far, so good? One thing that we want to do when we look at those polytopes is try to understand their geometric realizations. So there's, in 2004, there's sort of a famous paper by Jean-Louis Ledet, a French mathematician, who gave coordinates of the vertices of the associahedron. And remember, the vertices are one-to-one with binary trees. So he actually gave a recipe for, if you look at a binary tree, you can extract the coordinates in space, so that if you pick that point, the set of points corresponding to all binary trees on n nodes, you take the convex hull, you get the associahedron. And the recipe is really simple here. You look at every node of the binary tree, and you look at the left subtree and the right subtree. You look at the number of leaves of those. And the ith coordinate is the product of the number of leaves on the left subtree and the number of leaves on the right subtree. Okay? And you do this for every node I in n, and you get a vector in dimension n. And you take the convex hull of all those vectors, and you get the associahedron. Okay, so this is very simple recipe for computing the coordinates of the vertices of the associahedron, okay? So for all binary trees with n internal nodes, you just take the products of L and R and coordinate I, which are the number of leaves of the left and right subtree of node I in the tree, okay? Very simple, very clean. This is the famous like realization of the associahedron by Laudet. And not all geometric realizations of the associahedron are equivalent. And so if you talk about the actual geometric objects, you may want to talk about the Laudet associahedron. Laudet associahedron is the one that has these coordinates, exactly. Product of number of leaves on the left and on the right for every node of the binary tree. Okay? Okay, now I started with permutations and then looked at binary tree, showed there was a quotient operation going on, congruence operation going on. What about rectangulation? I promised you rectangulation. Well, actually, you can think of some equivalence classes of rectangulation as pairs of binary trees. So take one binary tree, like the top red thing, draw a right angle at every internal node. Okay, so when you split, you have a right angle. And then draw the leaves all on the same level on the horizontal line. Now glue two such things together, one upside down. If you're lucky, it's not always the case, but if you're lucky, you can tilt the whole thing 45 degrees and get a rectangulation, right? Now, this doesn't work with any pair of binary trees, right? See here, you see my mouse cursor, right? This thing is going to the right, so this thing must go to the left, right? So whether the leaves are a left child or right child must be preserved somehow, right? Otherwise, you would have an angle there, which wouldn't make for a rectangulation, right? It's an easy to state condition. It's about the signature, like whether each of the leaf has is coming from the left or coming from the right, and those two signatures have to match, right? If they match, then you can glue together the two binary trees and you get a rectangulation, which has the feature that every rectangle intersects the main diagonal here, the dashed middle line, right? And those are called diagonal rectangulations. So what I try to convince you of is that these diagonal rectangulations are just pairs of twin binary trees. So pairs of binary trees that you can glue together this way, where the leaves have matching orientations. Okay? Now let's explore the geometry of this. Actually, you can think of diagonal rectangulations as being canonical representative of equivalence classes of arbitrary rectangulations. So let's look at one rectangulation. Let's say that if we slide the walls, like if we move the segments, the horizontal segments up and down, or the vertical segments right and left, adjusting the length of the other incident segments, we can change the size of the rectangle. But there's some combinatorial properties that will not be able to change this way, right? And those combinatorial properties are like, if a rectangle has to be on the left of another one because they're separated by a segment, it will always be the case, even if you slide the segments in this way, right? So there's the right and left relation that is preserved. Above, below relation is also preserved, but adjacency is not necessarily preserved, right? So those two things on top are equivalent. We slide, the horizontal walls vertically like this, and now it's not true that the adjacency graph is preserved, but we will say that they're weakly equivalent. The two rectangulations are weakly equivalent in that sense, okay? And now the rectangulation on the left there is weakly equivalent to the diagonal rectangulation on the right. And it's true that for any rectangulation you can think of, it is weakly equivalent to a diagonal rectangulation, one of those rectangulations that you get by gluing two binary trees, okay? And now those equivalence classes that we call weak rectangulations, which are really sets of equivalent rectangulation with respect to wall slides, they're one-to-one with so-called Baxter permutations. And from Catalan combinatorics, you go to Baxter combinatorics, which is also a whole subfield, really. Lots of combinatorial families there are counted by those Baxter permutations. I use this vincular notation. You see that 4, 1, and 1, 4 are in green. And I mean that for this pattern to occur, where 4, 1 are in green, I want that the elements playing the role of 4 and 1 are contiguous, really next to each other in the permutation. Okay, this is so sometimes you use underline or overline or a dash between them. I use green to say that in the pattern, if it occurs, 4 and 1 have to be next to each other. So these are famous family of permutation. And again, we try to play the same game, showing there's a weak order congruence that we call the weak rectangulation congruence. And the word weak here is used in a different way. And using, some known result on quotient-topes, we'll try to have a look at what the rectangulotopes are. And this is a new word, right? Those are the polytopes, the generalized or deformed permutahedra that we obtain from rectangulation. In those cases, from equivalence classes of weak rectangulations. Okay, so first of all, how do we go from rectangulations to permutations? Remember that in the case of binary trees, we looked at the binary tree, we labeled it in order, in symmetric order, and then we looked at linear extensions, and those were our equivalence classes, right? Well, we'll play the same game here, except that now we have two trees. Well, look at those two trees, make a partial order out of them, and look at the linear extensions. And if you think a little bit, if you take the union of the two trees, what you have is the adjacency relation between the rectangles. And what you really need to think of in that case is the adjacency poset of the rectangles in the diagonal representative of the weak equivalence class. Okay, so you look at it suffices to look at diagonal rectangulations because, as I said, every rectangulation has a weakly equivalent diagonal rectangulation. You label them, you label the rectangles from the order in which they meet the diagonal, just like that. And then you look at the adjacency poset, which is pictured on the right there. And now you look at all the extensions of this adjacency poset. And these will define congruence classes. So these posets have been called Baxter posets by Emily Meehan in a paper in 2016. So it's not, it's not completely new yet. And so they're well understood. And if you play the same game and you look at those congruence, these equivalence classes, you can realize this is a lattice congruence of the weak order. Okay, so you can again collapse the equivalence classes of permutations that are linear extension of the same adjacency poset, and you get the weak rectangulation lattice. Right, so this is a quotient of the weak order. You can see that if you compare with the Tamari order, you see actually the equivalence classes are small because there still are many diagonal rectangulation, but actually two are missing. So there's a pair of there are two pairs of permutations that yield the same rectangulation on four diagonal rectangulation on four rectangles. Okay, so there I described how to get the set of permutations from the rectangulation. What we did what can be done, what has been done, actually, we did it for strong rectangulation, for weak rectangulation has been done by Shirley Lowe and Nathan Reading. We can go from any permutation to a rectangulation. There's a simple construction algorithm that constructs the rectangulation from the permutation. You can go back and forth between those two. So it's surjective, but it's not bijective. And now if you look at the equivalence class, you get this lattice. And, it's a lattice congruence, so it's a lattice on diagonal rectangulations. And it was known from this paper I just mentioned by Shirley Lowe and Nathan Reading that this again is a congruence, and that even before the general construction was known, they identified the polytope, which is the weak rectangulotope. And remember that associahedra are constructed from binary trees, that diagonal rectangulation are constructed by pairs of twin binary trees, like two binary trees and one is upside down. And then there's sort of a nice geometric materialization of this in the description of the weak rectangulotope, which is it is the Minkowski sum of two opposite associahedra. Right? So diagonal rectangulation is gluing together two opposite somehow binary trees. And the weak rectangulotopes are Minkowski sums of two opposite associahedra. Right? And this has been known for a while. And so here's a nice picture of the weak rectangular tope. And just like the skeleton of the associahedron was a flip graph on triangulations or a rotation graph on binary trees, here you have a flip graph on diagonal rectangulation. This is well described. So you can see, for instance, that from going from this rectangulation where all, only horizontal segment to this one, you just flip the top one and you flip it from horizontal to vertical, right? And all those flips are well understood and they're elementary local operation on the rectangulation. I'll show a general picture later of what the flip operations are on generic rectangulations. Any questions at that stage? Sounds good. What we did recently, I mean, it's kind of implicit in previous work, but we made it explicit. We convinced ourselves that this work is, together with Vincent, is that we wrote down what are the low-deck coordinates of the weak rectangular topes. Remember that low-deck coordinates for the associahedron were multiplying for each coordinate, multiplying number of leaves in the left and right subtrees. Here you do the same, except that you subtract on one hand, you compute the product of the number of leaves in the right and left subtree of node I. You do this in the top tree, and then you do this in the bottom tree, and you subtract the two. And this is the ith coordinate of the vertex corresponding to this rectangulation in the weak rectangular tope. Okay, and this is essentially writing down that this is the Minkowski sum of two opposite associahedra. So these are the coordinates for one associahedron, and these are the coordinates for the opposite associahedron, hence the minus sign there. Okay. So if you give me a diagonal rectangulation, I can very quickly compute its coordinate in space, so that if you do this for all rectangulation, take the convex hull, you get the nice polytope that I just showed. All right. So what if we don't admit that, I mean, what if we don't want to lose the adjacency relation between the rectangles, right? Now we look at a finer grain equivalence relation among rectangulation. We say that now those two things on top, they're not the same, right? So you can do wall slides, you can wiggle the edges and the segments, but you cannot change the adjacency graph of the rectangle, okay? So it's a finer equivalence relation, right? So there will be more people, okay? So now it's not true anymore that the one on the left is equivalent to the one on the right, right? It was a bit too much, right? We don't want to say that those two things are equivalent, right? We want to preserve the adjacency, not only the left-right, above-below relationships, but also the adjacency graph of the rectangles, okay? And this is a more complicated object, obviously. It's been proved by reading in his paper titled Generic Rectangulations that those were one-to-one with two Clump permutations. So they forbid sort of a generalized Baxter pattern or set of Baxter patterns that involve 5 elements. And again, I use the vincular notation here, that 5, 1 need to be next to each other. Okay. And so he proved this bijection. This is a not very well-known family of permutation. I don't know of any other major, interesting bijection between some combinatorial family and this family of permutations. So this is really newer. Let's try to play the same game. They're showing that there's a congruence and then that there are, polytopes on strong rectangulations. And this is the most recent part, right? I mean, so far it was sort of around, it was known, you could find this information in quite a few previous papers, but those haven't been explored as much. So remember that, again, for binary trees, I looked at them as partial orders and then look at the set of linear extensions. For diagonal rectangulation, I look at the adjacency relation, made it a poset, look at the linear extension of these posets. And I'm going to do the same thing. I'm going to express the congruence class, the equivalence class of some congruence relation as set of linear extension of some poset based on the input rectangulation. So I'm going to look at two things. First, the adjacency poset of the generic rectangulation. Remember, it it's not diagonal anymore because it's not true that there's always a diagonal representative. So I look at the adjacency poset, I orient it like I did before, right? From bottom left to top right, meaning that something that is above is higher in the order and something that's on the right is also higher, right? So I orient the adjacency poset like this. And you see I omitted the transitive edges, right? So this guy is below the other one, but you can follow the arrows. So this is not a relation in the cover graph. Okay, and to this adjacency poset, it's not enough. To this adjacency poset, we add those two special relations. Whenever you see two rectangles in this way, then the one on top should be above, even though it's on the left, right? So it's not, but it's not adjacent, right? So it's not in the adjacency poset, but it's on the left of a segment. And there you add also these special relation from the top rectangle to the rectangle on the right and at the bottom. They're not adjacent, right? So they don't form a cover relation in the adjacency poset, but they should come in that order in our new poset. Now, if we extend the adjacency poset with those two special relations, we get the thing on the right. On this example, it's a partial order that we can prove, and we call it the strong poset. This is something that we figured out was the right object to look at together with André, Stefan, and Eric last year. And now we are going to be able to say that linear extensions of these strong posets form congruence classes of the weak order permutations. And this is what we get when we're doing the quotient. Okay. That figure, I must say, is actually the same as the weak order on permutations because we only have 4 rectangles. I think the next step is 5 rectangles, but then we have like more than 100 of strong rectangulation. It's really hard to see. But well, I ask you to believe me that indeed we have something that is a congruence relation there, and we get some coarser, in general coarser, at least from n equals 5 on, coarser lattices than the weak order on permutations. And so we have this new strong rectangulation lattice. Okay, and because it's a congruence of the weak order, we can construct rectangulotopes, right? And those are the strong rectangulotopes. And then we can just say they exist. They exist thanks to, you know, there's this general result that I showed you. There's a congruence of the weak order, then there must be a polytope whose fan is whose normal fan is the fan of the congruence. And then you get you again get the skeleton is a flip graph. And what are the flip operations between the rectangulations? These are the 4 types of flips that you can get. So the one I think I mentioned is the simple flip. So if you have like I on top of j and they're adjacent, they form a big rectangle. You can flip this middle thing into a vertical one like that. But if they form an L shape like this, then you can rotate the middle segment, right, from vertical to horizontal, and one endpoint remains the same. Or same here, symmetric picture. If there's a vertical one, you can rotate it, making a horizontal one. So those are sometimes in literature called pivoting operation. They're the simple flips. And then there's a vertical wall slide that changes the adjacency, right? If we move this segment, the top edge of rectangle J up from, and we make now, we can make the rectangle J adjacent to I while it wasn't before, and vice versa. And here I and J are not adjacent, but by sliding the right edge of I, we make it adjacent to J, right? And those are all the type of flips, very natural local operations you can do on a rectangulation. And these are the changes. These are exactly the boundaries of the cones that like the analog of the cones that I showed you for the braid fan. This flip graph has been described by Emil Meehan in a paper from 2019, and we recovered it with our new ways of writing this bijection. And so you can check that those edges, each of those edges correspond to one of those 4 operations. Then together with Vincent recently, we thought, okay, can we give a better description of this strong rectangular top? Like, can we give low-day coordinates of the vertices? Can we give the equation of the facet-defining hyperplanes? And we did this, and I think this is the first time that it's described that precisely. This is a work in preparation. And for this, we use the theory of congruences of the weak order. I'm going to be shallow here. I'm going to hand wave a lot. I don't want to give you full definition. It would take too long, but just maybe sort of a flavor of what is going on in this beautiful piece of combinatorics, which is the combinatorics of congruence of the weak order. So there's this paper by Nathan Reading in 2015 where he showed that we can actually encode congruences of the weak order in a very nice and elegant way using what he calls arc diagrams. So you write, n dots on the horizontal line, and you say that an arc is, a curve that's connecting two of those dots, and it's going from left to right, and it can go above or below and wiggle any number of times between those two endpoints and go above and below any subset of the points in between. Okay, so for instance, it can go below all of them, or it can go above this one and below this one, or below this one and above this one, or above all of them, and so on. And it can go from any point to any other, from left to right. And there's a natural partial order on those arcs, which is obtained by taking sub-arcs. So if you take this big arc that go below all the intermediate 2 points here, and you cut it at the third point, you get an arc that goes only from one, the first dot to the third one. And the operation there is taking sub-arcs. Okay, so you cut. So for instance, this one, you can cut it, after the second dot and get this arc. Okay, you have to reconnect to the next one. But really, there's a partial order. There's a simple partial order on those arcs that is just taking sub-arcs. One arc is a sub-arc of another. And what Reading showed is that congruences of the weak order are one-to-one with poset ideals of this partial orders, right? So order ideals, so down sets that are downward closed. So if you take an arc, you must take all its sub-arcs. And for any such downward closed set, down set of this poset on arcs, you have a lattice congruence of the weak order, right? So those are one-to-one. So if you study the weak order congruences, you want to study those R diagrams. These are the same objects. And then even more recently, what Arnaud Padrol, Vincent Pilot, and Julian Ritter showed is that they could construct for this congruence defined by an arc ideal, they can directly construct the corresponding polytope by just taking the Minkowski sum of what they call shard polytopes that correspond to each arc in the collection given by the arc ideal. So you take your arc ideal, you downset in the arc sub-arc order, and then for each arc in this arc ideal, you have a small polytope that's called a shard polytope. You sum Minkowski sum all of those, and this is giving you the quotient tope of your congruence. And so this is in 2 slides, recent and very beautiful theory of the weak order congruence. And thanks to this theory, we could compute exactly what is the vertex coordinates and the hyperplane inequalities defining the strong rectangular tope. So in particular, what we have is that this formula for the coordinates of the points corresponding to a rectangulation, the point corresponding to a rectangulation R, a generic strong rectangulation R. And you see that you have the difference between two coefficients like we had for the weak rectangular tope. So there are, again, Minkowski sum of two sort of equivalent things, but upside down. And each of those things is a product. Again, I'm skipping details here, but just to give you the flavor of the formula, is a product between 3 things. And one is, again, for binary trees, defining this rectangulation, number of leaves in the right subtree, number of leaves in the red subtree, and then number of common leaves between node, the subtree, one subtree of node I in one of the tree, and one subtree of node J in the other tree. So now you have a product of 3 terms instead of 2 and a difference of those. And this is weighing the difference, EI minus EJ. So this is, you must add this weight to coordinate I and subtract it to coordinate J. Right? So it's a slightly more complex formula. And the subtrees of which we're counting the leaf, the common leaf, the leaves in the subtree, well, they're just generalization of the twin binary trees that we used to have for diagonal rectangulations. Remember diagonal rectangulation, twin binary trees glued together? But now the rectangulation is not diagonal anymore, so it's not as nice. So you see that some subtrees are actually, growing along the subtrees of the other tree. But those 2 trees are well defined. They still are there. And you can count the number of leaves and you can check the number of common leaves and so on. So you can get a complete geometric description, a vertex description of the strong rectangulators by counting and multiplying the number of leaves of those 2 trees. So I spare you the definition, the exact definition of those 2 trees I construct, but just remember that somehow it's obtained by taking the twin binary trees corresponding to the diagonal representation and then sliding the subtrees along the wall slides that you need to do to get to the rectangulation you want. Okay, we call them intertwined binary trees from now on. But well, we have still a formula, that we can write down. Each of those terms, sometimes, I mean, depending on the relative position of the rectangles, we don't have to sum them always, but it's intended to be something that you can compute directly just by looking at the rectangulation and looking at all pairs of rectangles in this rectangulation. Okay, so let me conclude. We get, I mean, I wanted to give you a flavor of some kind of a set of unified descriptions of bijections between equivalence class of rectangulation and class of permutations. Remember, we started with permutations defining binary trees, so forbidding a pattern of length 3, to Baxter permutation, and then we had 2 Klump permutations. And okay, there are many other bijections we can do. So in my paper with André, Stefan, and Eric, we identified more bijection by forbidding other patterns in permutation. In particular, we get a new class of so-called strong guillotine rectangulation, where we use strong equivalence, but we want the rectangulations to be guillotine, so to be recursively obtained by either cutting horizontally or vertically. So see the paper for more of those. There's some piece of analytic combinatorics and enumeration results also. And we also get complete description of 2 families of polytopes for 2 natural equivalence classes of rectangulation, one preserving only left, right, and above left, left, right, and above below relations between rectangle, and one preserving also the adjacency of the rectangles. And I'm currently writing a paper with Vincent on that. And yeah, this was what I wanted to show, and I thank you for your attention.